raise, but in the last 1.5 years, they are giving yearly raise of about 2%. So, but if it is this particular month, I don't. Usually they send an email about this to the specific set of people. I don't want to give any wrong information. Nothing that I know. Hello, Niranjan.
Good morning.
Hey, good morning. Let's see how it goes. Okay. Anything you guys want to say? There are 2 weeks of classes remaining. We'll have an exam on Friday on the week of exams. So there will be no classes during the week of exams. Office hours are also not obeyed as far as the times go. If you want to meet me, you will have to write to me. Usually everything is different in the exam, so that is applicable for any course in general. The office hours, you will have to ask the instructor when you meet. I posted a homework. Homework 11 is due today. And if there is, I think I'm pretty sure that there will be a take-home component to the exam. If it is there, it will be before the exam. Okay, that means to say that you work on the questions, whichever is take-home part, and then submit it with your exam at 10 o'clock. Between 8 to 10, I expect you to do about 2 problems, maybe 2 short, very short problems, and more concentrate, or let's say there will be 2 questions in the final exam, probably one from before midterm 2, one after midterm 2, so that way you spend main idea is that you try to go over all the content, and total there will be I expect there will be about 5 questions with take home, so 3 questions will be take home part. Okay. And let us also say the take home part, you can, it's like homework, so you can talk to each other. So that sort of gives it. Otherwise, there's always this challenge that some will look at it and then it's not fair. That's fine. Any questions on that?
What's going to be on homework 12?
What's going to be?
The topic for
Whatever I'm going to teach today. Not really today. So the idea is, I mentioned this last time, that most of the Green's function that we did last time was related to one particular differential equation, which was the harmonic oscillator, right? But look, instead of looking at it as a differential equation, think of it as a solutions. Solutions were exponential functions, which are Fourier functions, if I were to say. So if you have a space, typically there are two independent functions. And the basic idea was you read a times exponential plus b times exponential, and then you matched conditions, right? We will do the same thing, but now with Bessel functions. And which Bessel functions? Today I will do the normal usual Bessel functions, but your differential equation or the homework will be on modified Bessel functions, which is equivalent to saying you have trigonometric functions like sine and cosine. And the hyperbolic functions are when you put an I inside it, right? When you have imaginary variables, then you say it is hyperbolic trigonometric functions. Easiest to see is exponentials, exponential of I x, right? This is oscillator. You can say this is a standard trigonometric function, but you can have the plus or minus two functions. You can also have plus or minus x, that is hyperbolic. Similarly, in Bessel functions, you have two functions, two Bessel functions, which are usually oscillatory, exactly like sine and cosine. They are oscillatory, but not necessarily sine and cosine. They're not sine and cosine, but they have some connection with it. You make it hyperbolic in the sense you put an imaginary number in the argument, then it becomes like exponential, it grows. Like one grows and one decays. And this is what you will be doing in your homework. This is what I will do in there, but in context of Bessel functions. And have an idea of how they go, because exponential functions, when you have the graphs in your head, it is good. So same thing with Bessel functions. In your homework, you will do some plots of Bessel functions, and that will be useful. Okay. So Green's function associated with modified Bessel function will be your homework. And it becomes relevant in electros or any cylinder geometry. Any cylinder geometry will involve Bessel functions in the radial direction. If your physics is happening in the radial direction, then it will always be Bessel functions. Maybe that makes me give you some more hints on the broad idea. Whenever a variable, let's say z, goes from, let's say, all the way from plus infinity to minus infinity, then the functions you're interested in is plus or minus ik z. K is the label for the function, and these are Fourier functions if you want. Any variable, it doesn't have to be x, y, z, any variable. If it is going from minus infinity to plus infinity, then the functions that should come in your mind is Fourier functions. Okay? It doesn't mean that that is the only possibility. That's one good representation. It's like saying you have rectangular coordinates, cylindrical coordinates, and spherical coordinates. Whenever you have some spherical geometry, you think of spherical coordinates, right? You can do it in rectangular coordinates, but it is easier in spherical coordinates. Same thing, whenever you have a variable in this form and you have a function f of z, then you will expand this function in terms of this special functions, which are also the components. We'll talk about that. Another possibility is that z or phi, right? Doesn't matter. I can write this as z phi itself or z itself. This is less than some number. In this case, it is 2 pi, right? Angles, think of, so there is a limit on that. And this is less than or equal to 0. So this is what's the difference between these two? This is infinite range, or the domain is going from having an infinite region, and here it's a finite region. And in that case, here again it will be exponential, but this time the m will go from, so maybe I should say m will be 0 plus or minus 1 plus or minus 2 and so on. And here I should have specified k here. Is it readable? No. Here k goes from infinity to minus infinity. So this is k is continuous here, m is discrete here. So this is called discrete Fourier functions. These are called continuous Fourier functions. So whenever you have a function going from minus infinity to plus infinity, you go for continuous Fourier function, otherwise it's discrete. And then you have one more variable in rectangular and actually cylindrical coordinates. This goes from infinity and it is half region, right? That on one side you have infinity, on the other side you have only 0. Whenever you have this kind of situation, and it happens both in cylindrical coordinates and spherical coordinates, then you have Bessel functions. And the Bessel functions usually are, today I will talk in terms of one kind of Bessel function. Let me say just modified Bessel function. So usually you will say this is I m of rho, and this will be km, where m again will go from discrete quantity. So this you want to have a rough idea of this. It comes from experience. In the beginning, no one tells you this, but after a while you realize that this is what always happens, that whenever you have such coordinate distribution, then this is how you will go about. It's always, there is one more interesting feature. What if this was discrete? If the original parameter itself is discrete, then again it is discrete, but then this is not, phi is not a continuous variable, it is actually discrete. And then the roots of unity that we did in complex numbers, that comes into picture. We did a little bit of that when we were doing unitary operator basis, and that plays an important role in, very broadly speaking, quantum computing. Like quantum computing does a lot of Fourier transformation, and they happen in discrete Fourier transformations. And in that case, phi is discrete, and the roots of unity plays an important role. Okay, so this is modified Bessel functions. That's what your homework will be about. Here we will talk about Bessel functions. But let me remind you very quickly on Fourier functions. Right? So this is Fourier functions, just to give you a feel for what is the idea. As I said there, let me first we have to define our functions. So let's say phi is going from 0 to 2 pi. And we have functions which are e raised to I m phi, where m can be discrete, plus or minus 1, plus or minus 2, and so on. So that's your variables, if you want. And these are called the Fourier functions. Now, if you remember, when we were doing vector space, we recall, right? So we spent a good bit of time on this. We said that if there is a basis, E I, let's say, so let me put it as, yeah, E I, and Let me just have one point. So this is your basis. Is that a vector or a tensor? Like, this is a mixed notation, remember? There is a vector sign there, which is representing one index, and there is another index I. So this is a tensor in principle. Okay, so there is 3 vectors, each one having an or I has the index and the vector sign itself has a vector. So this is a mixed notation. So three unit vectors, right? That's all you need to realize. But it's a tensor. But how do we do this? The vector space idea is this is the only I'm going to write the whole of vector space ideas in one line. This is A. This is equal to A dotted with 1. But 1 has a completeness relation in it. 1 is E1 plus E2, E2 plus E3, E3 if you remember. That's equal to, let me go 2 lines. This is equal to E1 plus E2, E2 plus E3, E3. That's completeness. Okay. This is equal to 1 is a relation that comes with this. When I say these are basis vectors, they satisfy this. I give you this also. Basis vectors comes with a completeness relation. Basis vectors comes with an orthogonality relation. If that is the case, and again, what are we saying? Given any vector, I can write it in terms of this, any vector. That's the statement, and that is the idea of completeness. And now you say that this is A1, E1 plus A2, E2 plus A3, E3, where A dotted with, so notice this is the dot product, this is E, will be A, oh, A1, oh, you're saying, good, thank you.
Dr. Rajesh, can you try to zoom a little bit?
Oh, zoom, oh, so this is,
It looks blurry.
okay, here it is clear, that's weird. Better?
From my end, it is not that clear, but it's fine. It may be with this something with the zoom.
Ah, interesting. Zoom it, it's very clear for us, I think so, at least.
Okay, that's fine. That's okay. I can read now, but
My eyesight is better. And it is reacting very slow. Okay. Better?
yeah, it's fine. Thank you.
This is A dotted with the I, right? So that's the I. Okay. This was the idea of vector space, right? Completeness, and we have also there is an inbuilt orthogonality in between. So functions or basis vectors. So basis plus completeness plus orthogonality. Okay, that's what you need to be able to write any vector in terms of basis vectors. Vector, completeness, and then you have components. If I know A1, A2, A3, I know the vector. So this has the information about the vector. In this basis, components of vector A in the basis E1, E2, E3. Now I'm going to do the same thing in function space. So we can call this Hilbert space or function space. This is often the Hilbert space. Okay. I need to provide my basis. This time we will say functions, special functions. So Fourier functions. So this is the basis function. The basis will be e raised to I m phi. So that's my basis. Again, I need a completeness. Plus orthogonality. Here the completeness was a summation in I. So let me give the comparison. E raised to vector I and let us say I. This will lead to exponential of I m phi. Oh, I have to move the camera. Sorry.
Now it is very clear.
No, but I went down, I think.
Yeah, you can zoom out a little bit if you want to cover more space.
I'm going to set this. I think the camera is
Okay.
at a weird angle. So now I can move around. No.
Suddenly everything looks clear.
Clear.
Mhm.
I'm just setting it. Okay.
Yeah, thanks.
Okay. So we had this basis vector here. Notice there is this I and this vector symbol, right? This one will correspond to M here. Okay. Whenever you want to have a visual feel for what it is, that's going to be your M, and this vector here, that's your phi. Okay. Remember, your completeness was the I. So I sum over I. So notice this is summation over I. So let me write that explicitly. This is let me not write that. Okay. This is summation over I. That's understood, right? Whenever I'm repeating the I, there is a summation over I. This will correspond to I have a summation over M. E raised to I m phi and another e raised to I m phi. So this is now notice when I'm writing this, I have different indices here. So I need to keep the different indices there also. So this is I m prime times phi. Or m is being summed, so it should be the same and phi prime. One of them has to be complex conjugated, so I'm going to complex conjugate this. We did this when we were doing unitary operators, that one of them should be complex conjugated. Vector space usually is in real space, then we don't worry about that. Maybe if you want, you can say this is star, right? That's complex conjugate. This is the complex conjugate of that, and then you sum over m, where that is m running from minus infinity to plus infinity. And we also have one more relation, orthogonality, right? This is I dotted with j. This time this is star here. I think this one is the opposite. This is. And this is the orthogonality, and this will correspond to, now I have to dot this, so this will be an integral in phi e raised to I m phi star and e raised to I m prime phi. Notice I and a j, m and m prime. Is that readable? Okay. So it means to say that I should know what these integrals are. So let me do that very quickly. And this is our Fourier space, then we want to do this for. Hopefully this will be better. Oh. So orthogonality of Fourier functions is, again, as I said, you start with e raised to I m phi, then you do e raised to I m phi again, but you want to say this is m and n prime, and you integrate over phi, and that is a start. Phi goes from 0 to 2 pi. This is the generalization of one vector multiplying with the other vector and the dot product that we do whether they are orthogonal or not, we have to check. So for each m, remember these are the Fourier functions where m is the label for that. For each m, if m and m prime are the same, it should come out to be 1, otherwise it should come out to be 0. So is that the case? So let's do that, and let me also do one more thing. Just to normalize that, let me also put a 2 pi in there. That's equal to 0 to 2 pi, e pi over 2 pi, and this is nothing but e raised to I phi times m prime minus m. What is that integral equal to? Delta function. Yeah, you're thinking a little better.
Delta m prime minus.
It's very good. Yes, that's correct. And why is that? Maybe you can elaborate a bit. So if, let's think of, if m prime was equal to m, that's one possibility. I think that's what you're thinking in your head when you say delta. If that is the case, then this is having a simpler set situation because this is now 0, right? Then this is 0 to 2 pi, e pi over 2 pi times exponential of 0 is 1, so that's just 1. That's what happens when m prime is equal to m. And if m prime is not equal to m, then I can just integrate that. It's an exponential. It brings m prime minus m in the denominator. when it's in the denominator, I should be careful. That's why I did that separate. So if I now do the integral, so this is e raised to I phi m prime minus m over 2 pi I times m prime minus m. It comes in the denominator, which if it was 0 will be very bad. So that's why I did that particular case separate. That is equal to, this is easy. That's equal to 2 pi integral divided by 2 pi, that's 1. And here you have, when phi equal to 2 pi, whatever this is an integer. M prime minus m is an integer, and 2 pi times an integer is equal to 1, right? Complex number, that's equal to 1. And this is also equal to 1. So these give you the same numbers in the lower and upper limit, so it is 0. So that's equal to 0 if this is m prime is equal to m, and this is m prime not equal to m. And that's symbolically written as delta m prime, and that's what Aryan was pointing out. Good. And that's orthogonality. This is orthogonality. You should compare this with e raised to I, or the vector index, right? So this is e raised to I dotted with e raised to, what should I say, the basis vector labeled with I dotted with the basis vector labeled with j as delta ij as the product. Notice, take two vectors, take a dot product, it is either 1 or 0. Same thing here, take two basis functions now, Fourier functions. If m is equal to m prime, that is 1, otherwise it's 0. Same idea there. So you want to keep that in mind. Now we want to do completeness, and we won't prove that here, but at least qualitatively you will be able to see that. So this is completeness. Of Fourier functions, and that is, you do sum over m equal to minus infinity to plus infinity exponential of I m phi. Now we are summing over phi, so I keep the other variable different. This is e raised to I m phi prime. And this comes out to be equal to delta of phi minus phi prime. And that is a 2 pi. So let's put a 1 over 2 pi. Let me check that. Make sure. Very well. As usual, I don't have my notes. I think that is 2 pi. Again, you can broadly see what is happening. This is a continuous delta function. This is phi is continuous, and here the property is that if phi is equal to phi prime, instead of it being 1, it is infinity, otherwise it is 0. And you can see that if phi is equal to phi prime, these two go away, and then there is 1 here. But now we are summing infinite number of ones, right? 1 plus 1 plus 1 plus 1. For each m, there is a 1. So that's infinity there. And otherwise, these are oscillatory functions. That is the harder part. But using roots of unity, you can show that this is indeed equal to 0. Remember that roots of unity is equal to 0. But let's not go in there. We have orthogonality. First, we talk about a function, orthogonality, completeness, and then there is a differential equation that each of these functions satisfy. That's differential equation, and that is easy to see. Take the second derivative with phi. And add f. So second derivative of phi will be I times m, and then you add this plus m squared. It is very clear what will that be equal to? What will that be equal to? It will be 0 because every time you take the derivative with respect to exponential, it brings down an I times m. I times m times I times m, that is an imaginary number. That's I square is equal to -1. So this is I times m squared plus m squared. E raised to I m phi, that's equal to 0. And that's a differential equation. And that's very similar to the differential equation we dealt with in our when we were doing Green's function. We started with this differential equation. Whenever you reach this is you are interested in the solutions, correct? If there are two solutions, you say that, oh, it is a times arbitrary constant times one of the solution plus arbitrary constant times the second solution. That's your total set of solution. And from there, you can do the same idea of Green's function matching conditions there. We will do the same thing now with a new set of functions, which is called the Bessel function. So now let me introduce what is Bessel function. So this is a broad idea of what happens. Okay. Bessel function of 0. Notice that naming Bessel function means this is j. That's your variable, that's the normal function, but then I say it is the 0th order, right? I think it is 0. That's the 0th order. Very quickly, almost immediately, I will talk about the mth order. That is J0, J1, J2, that is a whole set of Bessel functions, but that's the nomenclature. So how is this defined as? This is equal to, this is just a definition. This is the alpha over 2 pi exponential. This is 0 to 2 pi and I t cosine alpha. What is that integral equal to? You cannot do this integral. This integral cannot be performed using elementary functions. That is why we give it a name. Right? This is an integral which we do not know how to work with, but instead we say that we will call it this and find the properties of this function. Like, for example, sine function is a series. There is a series representation of Bessel function also, but whatever we do here in this course, we will do it using this integral representation. usually definition of a Bessel function, most of the traditionally, almost every textbook will do it using a series. Then the idea is that you want prove identities related to that. Then you start from the series, work out and find different properties of them. That's one way of proceeding. But a more modern way of proceeding is write the integral representation of that and do the same thing. Whenever you want the Bessel function, you write the integral representation of that. We will derive the series representation also somewhere about maybe 10 minutes, 15 minutes down. Is that clear? So that's the definition of Bessel function. That's your parameter t. That variable shows up here. And that's your integral. And this integral cannot be done. It seems like since there is an exponential of I, this might have a real and an imaginary piece to that. But Bessel function is a real function. So how do we show that? So let's do the imaginary part, right? The imaginary part of the Bessel function is equal to imaginary part will be, this is cosine and sine, right? Whatever comes in front of I, that's what will be the imaginary part. So that will be sine function. So this is 0 to 2 pi alpha over 2 pi times sine of t cosine alpha. That clear? So it's a sine of a cosine function, but then it is scaled with the parameter t. Also, if this is real, this should be 0. So let's show that this is actually equal to 0. So that's equal to break this into two pieces. So 0 to pi e alpha over 2 pi. And you have pi, 2 pi. That's a simple integral property I have used. And in the second piece alone, first piece, leave it as it is. I'll leave it as it is, 0 to pi alpha over 2 pi sine of t cosine alpha. Pi to 2 pi, make a substitution. Let's say this is pi prime is equal to alpha minus pi. Like that's just a substitution I make. And that would mean d alpha prime is equal to d alpha. So my second integral becomes, instead of d alpha, I'll say d alpha prime, 2 pi. The lower limit, when alpha is equal to pi, pi minus pi, alpha prime is 0. And when alpha is equal to 2 pi, alpha prime is equal to pi. And this is sine of t times cosine of alpha is pi times pi plus alpha prime. Cosine of pi plus alpha prime is nothing but minus of cosine of alpha prime. Sine of a minus quantity brings in a minus out, and then these two are exactly the same. That is an alpha prime, but that's a dummy integral variable. So these two are negative of each other. Right. So is that clear? One more step. 0 pi alpha 2 pi minus of 0 pi alpha prime over 2 pi. But the dummy variable doesn't matter, so these two are the same. So that's equal to 0. So if the imaginary part of a function is 0, that's equal to that's a real function. That's what it means. If that is the case, there is one more part that comes out very clearly, that this is also then equal to, I have to move the camera again. If the imaginary part is equal to 0, so we showed that the imaginary part of this is equal to 0, that means this is also equal to 0 to 2 pi, the alpha over 2 pi. Sine piece is 0, so it is simply the cosine piece that contributes, p times cosine alpha. Agree? Because the imaginary part is equal to 0. If that is the case, one thing you can immediately say, what if I were to put t equal to minus t? Cosine of a minus t is the same. So that means this immediately implies that J0, the 0th order Bessel function, is even. So, because if I substitute minus t, cosine function brings it out. This is the 0th order Bessel function. It immediately we should ask what is the nth order Bessel function. So let's define that. Bessel function nth order. Is it still fuzzy or is it really better now, Niranjan?
It's very good.
Okay, okay, yeah. But then you don't have the zoomed out bird's eye picture, right? That's it. Okay. Bessel function of the nth order is defined as Jm of t will be equal to 0 to 2 pi. I'm missing something here. I'll come back to that. I t cosine alpha, that's 0th order. The nth order is right minus I m alpha. If you remember, this is nothing but a Fourier function, correct? So in a way, nth order is the Fourier transform of this exponential I t cosine alpha. So that's another way of thinking of it. If you're comfortable with Fourier function, if you have an insight with Fourier function. There is also one more thing. There is an I raised to m, so I should divide that out by I m. I often like to write the I raised to m on the left hand side, but since we are defining this for the first time, let me put it that way. And let me make sure that I'm not missing anything since it's a definition. If I have. Yes. Okay. That's your definition, and it is good. I said every time we have the definition of a Bessel function, there are two ways. The modern way is the integral representation, and the older traditional way is series representation, which is a lot more powerful because there is so much literature on it. Most of the proofs that is with integral representation is more recent, but everyone, most of the time, in the olden days, everyone used a series representation. So let's see. what is the series representation of this? First of all, we can also maybe say we can define the Bessel function in one more way, but let's call this the generating function. Of Bessel. It's almost the same thing, but you write it as a Fourier transform if you want. But so here it is. You start with this function e raised to I t cosine alpha. And you want to write this as an expansion equal to, you want to write this as a Fourier expansion if you want, equal to minus infinity to plus infinity and let's see, I want to write this as e raised to I m alpha times I m times j m p. But it's sort of you're separating the variables, all the there is p and alpha here. All the alphas are coming in the exponentials and p dependence is picked up in the Bessel function. So this is called a generating function in the sense that if I can write the series representation of this as a Fourier expansion, then the coefficients basically are the Bessel Bessel function, and this is basically the inverse Fourier transform if you want. If I were to isolate this, then I get the other side. Maybe it is good to see the connection between the two. So let me show you how this is connected. So what we can do is start from here and multiply I m prime alpha on both sides. I should move the pen. That's completely allowed. So this is and let me do minus I m prime alpha sum over m and this is a standard trick you use while working with Hilbert space, or it's not even Hilbert space. This is vector space, right? Remember, function, a vector, this is a vector if you want, is being expanded in terms of Fourier functions. Like this is the basis. Vector, basis, components. If there was a vector A, you will say X, E, basis vectors, and then the components. If I want to get the components out, yeah, let me do that very quickly. So A is equal to a I times EI, right? If I want to find the components AI, how will I do that? I will multiply this with EJ, right? And if you allow me to do that on the same on either side, then you say that, oh, that's delta IJ. So this immediately tells me, orthogonality tells me that's delta IJ. So that's AJ is EJ dotted with A. If I have a vector statement in terms of the components, if I want to find the components, I multiply the vector with the basis functions if you want, and it will pick out my component for me. This is a way of saying I'm inverting the representation of a vector. I want to do the same thing here. Vector, function actually. So that's the difference between a vector and a function, that these are infinite dimensional vector. Vector, basis, components. I want the components. I want the Bessel function. Right? So I'm going to multiply both sides with the Fourier functions, and now I have to use the orthogonality. What is my orthogonality? I will integrate with respect to alpha. So integrate with respect to alpha on both sides. The alpha over 2 pi, 0, 2 pi. Do this here. The alpha over 2 pi, 0, 2 pi. Again, have your dot product orthogonality in mind. This is your orthogonality, these two with an alpha. If you recall your orthogonality of Fourier function, when I add integrate over alpha, it was delta m prime, like that's what Aryan figured out, and this is equal to keep the summation intact. Basically, we are interchanging the summation. M is equal to minus infinity to plus infinity. The alpha integral is nothing but delta m prime, and this is I m j m t. Same thing we do in vectors also. When we take the orthogonality, it's only one piece that contributes. Here, only one contributes. Then m is equal to m prime, and that's the same as I m prime times j m prime t. So I've solved for my Bessel functions immediately. So that's equal to this. That is what we wrote here, right? E raised to I t cosine alpha, except that it is, instead of m, we have it as m prime. Okay. So in that sense, we can say that Jm is the Fourier transform of your e raised to I t cosine alpha. Again, that's it's also said it is a generating function, but it is basically the Fourier transform, the Fourier components. Yeah, instead of saying Fourier transform, it is the Fourier components of this particular function, and then you have this as a, so maybe state that. So I m j m t are Fourier components of exponential of I t cosine alpha. So that's another definition of Bessel function of m order, which is this statement, which is the integral representation. But I said there is a series representation also. So let's do the same thing. So we want to find this series representation in here, and it is expanded in e raised to I m alpha. So let's try to do that. Series representation. So let's have a label here. Whenever we have e raised to I m alpha, let's just e raised to I alpha here. And an I also. Let's have that. Let's call it U. Just a label so that we'll be doing it again and again. So exponential of I t cosine alpha which is the generating function of the Bessel functions. This is the same as e raised to it, e raised to I alpha plus e raised to minus I alpha over 2. The exponential of an exponential comes in. That's the same as like one more. So this is t by 2 comes in outside. You have I times e raised to I alpha, and the other term can be written as 1 over I times e raised to I alpha. And that's written specifically so that I can identify the u inside that. So this is equal to e raised to t by 2 times u minus 1 over u. Two exponentials, I know the expansion for exponentials. So let me write that again, e raised to t by 2 u and exponential of minus t over 2u. Two exponentials, and exponential has this expansion. So e raised to x is a summation of n going from 0 to infinity, 1 over n factorial times x raised to n. Right? That's the definition of the exponential as a series. So this is equal to two exponentials. So n going from 0 infinity, 1 over n factorial, here it is t by 2 times u raised to n, and another series, but this one is negative. Let me call that k. K equal to 0, infinity, and this is 1 over k factorial times minus t over 2u raised to k. I want to write this as a series in U because U is the expansion, right? So I want to write this as a series in U. So, let's collect these two terms together. I gotta move this maybe. So that's equal n equal to 0 to infinity, k equal to 0 to infinity. Collect things together. There is 1 over n factorial, 1 over k factorial, and then there is minus 1 raised to k. That is t by 2 raised to, there is an n here, k there. That is n. The minus I already pulled out, so it's n plus k. And u is n here, k. So that's there are two summations. So how do you deal with double sums and that too going from infinity? So one of the ways to count, right? So this is basically a matter of counting. We're not really going to evaluate anything, but try to resum it in a sense. So you can see. Okay. So we want to do this summation. So let's see where it is counting. So there's an n and a k. So let's say n is here and k is here. It's a discrete sum. It's starting from 0. And then you go 1, 2, 3, 4, 5, and so on. Right? That's your summation in k. N goes from n 0, 1, 2, 3, and so on. So every point in the first quadrant here, discrete point, contributes to the sum. idea is to add up all these contributions. So at every point, this has a value number, and I want to add that this plus this plus this plus this, and at each point I have to evaluate that. But when I'm adding, it doesn't really matter in which order I add. Here, what we are doing is that first fix n sum over k, next n sum over k, next n sum over k. That's the way this is being done. But that need not be the case. So that's what we are going to do. What we are going to do is we are going to do this diagonally. We want to do this sum diagonally. So let's see how you can do this. So let's make the substitution that we are interested in n minus k. Let's call that m. Okay, so n is equal n minus k is m. And if I want to see that where is that happening here, that's the same as n is equal to m plus k. Like that equation is the same as this. Look at it as a equation of a line, y-axis, and k is x-axis, and m is the y-intercept. Right? If you think of this, y is equal to mx plus c. Right? That's your c. That's your slope is 1. Right? Slope is 1. And c is the intercept. That means to say that what I'm thinking of is we have these lines. You can draw. These are all 45-degree lines because I want the slope to be 1. And the intercept decides where my m is. So this is m equal to 0. This is m equal to 0 because that's the intercept, right? That's going through the origin. This is m equal to 1. That's m equal to minus 1 because this is going at minus 1. Wherever it's cutting the y-axis, that's what decides that. And in general, I have m going from minus infinity to plus infinity because I want all these lines. It has to go from minus infinity to plus infinity. You can also see here that this can be both positive and negative. Right? So m goes from minus infinity to plus infinity. That's going to be my one way of summing. But then k, I will keep it fixed. So k, I'll keep the same k. So k will be equal to k. So that's my transformation if you want. So wherever I see n, I want to replace it. So my substitution will be replace n with k plus m. And don't do anything to k. Just keep k as it is, right? That's my substitution in here. And in that substitution, what is happening is that n still goes from, no, I'm not going into n anymore. So it is k still goes from 0 to 0, 1, 2, 3, so on. And m goes from 0 plus or minus 1 plus or minus 2 and so on. Right? Is that clear? Any comments or questions there? Is that clear enough? If I use that, I can put this back in here. If you allow me, I'm going to erase this piece here and use the space. So that I don't have to rewrite. So that's equal to keep the instead of doing n and k, I'm going k equal to 0 to infinity and m going from minus infinity to plus infinity. The main idea was to figure out where the summation goes. That was the whole breakup in here. From that point on, I just have to replace n with k plus m factorial, and k remains the same. We have minus 1 raised to k and t raised to or t over 2 raised to n is equal to k plus m, so it is 2k plus m, and I have u raised to n, right? N minus k is m. But that's my exponential. Let me go one step further up. I'm going upwards. So exponential of it is, rewrite this in the following form. M going from minus infinity to plus infinity. U of m, which is nothing but I. This is I times e raised to I alpha raised to m. Remember your u, right? It's right here. That's fine. U, I substituted that in here, and whatever is remaining is should be my Bessel function. Right? So this is k equal to 0, infinity 1 over k factorial, 1 over k plus m factorial, and minus 1 is k p by 2 uk plus. And this, whatever shows up here, with that I raised to m is my jm. Or actually, I shows up separate. So this implies, since think this one came later. So I have j of m as a function of t as a series representation is equal k equal to 0 to infinity 1 over k factorial, just copying from there, minus 1 raised to k 2 k plus and often sometimes, I mean, again, it depends on what kind of literature you have in your hand. Traditionally, if you want to prove any identity for Bessel functions, you will start from here and then use it. But what we will do most of the time is work with the integral representation. So this is the series representation. On the other side of the board, you see the integral representation of Bessel functions. And we will try to find the orthogonality relations for this and the differential equation. That's the two important things we have to find: orthogonality and differential equation. Once we have differential equation, we should just test. Just for testing purposes, it is good to find the Wronskian. Wronskian make sure that it is independent. If you have two functions, if they're independent, it is non-zero. So once you check that, then you know the solutions for the differential equation, and that's all you do. And from there, you do the same thing as we did earlier for the Green's function, which is your home. Okay. Yeah, that's all. Niranjan, I think you did very similar things with elliptic functions, so this might be very nostalgic for you. Okay, that's all.
Thank you, Dr. Solis.
Thank you. Again, you feel free to go ahead with your homework, because the homework is about hyperbolic Bessel function, which is called modified Bessel function. So I started with an integral, and then I worked with the integral. There, the integral will be slightly different, that's all. Otherwise, it will be very similar. So go and proceed and do it, because we won't see that in the class. But the ideas are going to be the same. Okay. Thank you. Here it's clear. It was not coming out clear there, no?
Maybe due to internet, I think.
Yeah,
Something
yeah,
lagging.
yeah.